And do you guys see that this equation, remember how I showed y'all on the other one, how it follows along with y equals mx plus b? Okay, do you see this one does as well, y equals mx plus b? So I am about to give y'all a little take-home assignment at the end of class where you got to graph some stuff. So what gets plotted on the y-axis?
The delta.
Do you see it's the reciprocal of the concentration? Because that's y. Equals mx. What gets plotted on the x-axis?
2.
Mm-hmm. And this will be, if the equation is second order overall and you plot this, it will give a linear line. It'll give a straight line. And do y'all see this line's going to point up? How'd you know the other one pointed down?
Is negative K.
Because it had a negative in there. This line's going to point up. And do you see still the slope tells you what the rate constant is? Okay? So that's the first order. I thought I had a second order one to work. I was going to work a problem, and I thought I had one written down, and I don't. So, sorry. We'll do this one. Okay. The rate constant for the following reaction, I gas and I gas makes I2 gas, is 7.0 times 10 to the 9th m negative 1 s negative 1. If the initial concentration of I is 0.086 molar, calculate the concentration after 2 minutes. So look, y'all, I just introduced the second order equation, right? That's what we're going to use. But you're taking a test. How do you know if this is first order or second order? There you go. Units of your rate constant tell you which one to use. Okay? So, what are you calculating? Do y'all see that you are calculating the AT, the concentration at some point in time? Right? Is equal to, I'm plugging into the formula here that I just gave you, K, 7.0 times 10 to the 9th. And we had to watch this when we did one on Monday, because my next variable to plug in is the time. What do I have to watch about plugging in the time?
Minutes and seconds.
The units, right? Because I gave you a 2-minute time, but the rate constant's in seconds, so that's 120 seconds, right? So that my units will match up. Plus 1 over, it says the initial concentration, which is 0.086. Then, this is what y'all are good at, the math, yeah? y'all get to this, 8.4 times 10 to 11. Okay? That's not the answer, though. What's the answer?
Is it 1 over that number?
It is. That is the reciprocal of the answer. So to get the answer, I have to take the reciprocal of that. So don't get in a hurry and stop there, because you're not there yet. I got 1.19 times 10 to the minus 12 molar. That's what I have.
Can't we just put that like over 1
Oh, I want it,
or under 1?
okay, I don't want it like that.
Okay.
Yeah, I guess in some calculus classes, are you required to report it like that, like in a fraction form, or
Yes, the number to be.
if it's too big? Okay. Yeah, I would want you to work it out, so. Because if you don't, I think maybe you don't know how to, you know?
Yeah,
I mean,
it's all perfect.
okay? Now, there's also a half-life equation for a second-order reaction. Did we do half-life?
Yes, ma'am.
We did. What is a half-life?
You said like half the time it takes for something to dissolve or something.
Yeah, it's the time it takes for the concentration to drop by half. Okay? So for a second-order equation, overall, the half-life is equal to 1 divided by K times the initial concentration. So, y'all, what we can tell from this mathematically, first order equation, I'm going to jump back to what we did last time. The half-life is equal to 0.693 divided by K for first order. K is the rate constant. A rate constant for a reaction doesn't change unless you change the temperature. So for a first order reaction, y'all, a half-life is constant. Like, I think I talked to y'all about radioactive isotopes and how they have different half-lives depending on what the isotope is. And it's always that. No matter how much radioactive isotope you have, like P32, the half-life is always 14.3 days. It's always the same no matter how much you start with. But do you see that for a second-order equation, the half-life not only depends on the K, but it depends on the initial concentration. And so after one half-life, you have a new starting concentration. It's going to be lower. Do you see that the half-life, it's not a linear correlation. For a second-order reaction, the half-life gets longer and longer and longer every time. Because after every half-life, you're starting with less stuff. And starting with less stuff makes this half-life extend. It's not a linear thing. Okay. Let's look at reaction mechanisms. When I introduced this chapter, I told y'all a lot of stories about like how ethanol is metabolized to acetaldehyde and then how it converts to acetic acid. And so it's a step-by-step process, right? It's not just one thing. Reactions happen that way as well. For example, if A makes B and B makes C, this might be a mechanism, a step-by-step for an overall process. What would the overall process be here? A to C. Okay? So A to C is your overall process, but these are your steps. These steps are referred to as elementary steps. Okay? In an elementary step, the rate law will follow the coefficients. You guys remember looking at data last time and we would say, oh, if the concentration doubled and the rate doubled, that meant it's first order. And we had to look at data to decide what the rate law is. If you're looking at elementary steps, though, For example, let me add something here. What if I'd said 2A makes B? Since I'm telling you that's an elementary step, you know that the rate law looks like this. Rate is equal to K times the concentration of A squared. You don't have to look at data for an elementary step. The rate laws, the exponents in the rate law are going to match the coefficients. I'm trying to read y'all's expressions, and some of those expressions look like I need a minute for that to sink in. Or maybe,
You might have to say
okay. Is it the test at 9:30 that's kind of got you like blah, 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 blah?
I think I was writing it down, so I didn't hear you say.
Okay, so if it's an elementary step, you simply look at the coefficients for the orders in the rate law. Okay? So what's the rate law for this one? This is an elementary step. What would it look like? Rate is equal to K times B raised to the first power. Okay? Now, do y'all see that B is showing up in my elementary steps? But it doesn't appear down here. B is referred to as a reaction intermediate. B is the reaction intermediate. The definition of a reaction intermediate is it's produced in one step, used up in a following step, and does not appear in the overall equation. Or I should say overall reaction. Reaction intermediate, produced in one step, used up in a later step, and does not appear in the overall reaction. And so in this example, B is your intermediate. Okay? Finally, when you have elementary steps, y'all, they can go at different speeds. Some can be fast steps, some can be slow steps. The slow step, I don't have room on the slide, so I'll just write it, because I'm afraid if I don't write it, y'all won't catch the importance of it. The slow step is often not called the slow step. It's often called the rate determining step. Okay? If you know which step is the slow step, the rate law for the overall equation will match the rate law for the slow step. So for example, if I gave y'all this problem and I told you that step 1 is the rate determining step, and then I said, here's the overall equation, A makes C, what is the rate law for the overall equation? You know what it is, because I told you this is the slow step. So you know the rate law for the overall equation is rate is equal to K times A squared. Okay? The overall equation rate law does not necessarily follow the coefficient. It only follows the coefficient when it's an elementary step. I promise it'll be an easy day. Hang in here with me, okay?
Will you always tell us which one the slow step
Yes.
and the rate determining?
Somehow I will tell you, okay? So sometimes I might say, how was it?
That test kicked my ass.
Well, I was recording.
Dude, I
when it
think I did all right.
Stupid, you can't cross those out.
No, well, I mean, I guess you could. So, what we were talking about is the rate determining step, and how, like, I told y'all just a second ago, and I circled it in blue. I said that's the rate determining step, and then you'll be able to catch up when you watch it. And then so y'all knew the rate law of this, and so you said, will you always tell us what the rate determining step is? Maybe not. What if I said the rate law for this equation, A, make, and C, is this. And then I said, which step is rate determining? But it's just reversing what I told you, okay? So let's practice one. The following are elementary steps. H2O2 plus I negative yields H2O and IO negative. And H2O2 plus IO negative yields water and oxygen and I negative. Number one, I want you to write the overall reaction. Okay, so the overall reaction is 2 H2O2s yields 2 H2Os plus O2. Is that what y'all got?
Show me how you did that.
Okay, so when I put a box around this one and this one, that's kind of showing me they're gonna cancel out. If it's produced there and used here, cancel them. And then I circled purple these to show if there's one over here and one over here, those are gonna cancel. And then I summed up, like there's 2 H2O2s and then 2 waters. Okay, so that's how I get overall equation. Granted, it's probably easier with A, B, and C. Yeah, much simpler, but. Now, when you write the overall equation, y'all see why I put a 2 here, right? Because there were 2 hydrogen peroxides. Look at this thing in purple. Do y'all see that it's balanced like it is?
Mhm.
If you do it right, you shouldn't have to fix any of that. It ought to be balanced when you write it, okay? So are we good now that I've shown you what that is? That's easy?
Is that same stuff from chemistry 1 that we were doing?
Kind of, sort of. It's kind of like Hess's law.
Yeah, that's right.
Yes, it is kind of like Hess's law. Okay, second question. And I threw you a curveball here, so don't. Are you supposed to swing at it or not?
Oh.
Okay, don't swing at it. You can hit a curveball, right?
You can hit it, yeah.
Yeah. Okay, identify, because sometimes they're curving, they're coming into the strike zone, right? You better swing when it gets there. It depends.
If it's a good ball, hit it.
If it's a good ball, hit it. There you go. Okay, identify the reaction intermediates. What did I tell you an intermediate was?
You wanted to tell what's
It's
different.
the, yeah, produced and used up.
Produced in one step, used up in a later step, and does not appear in the overall reaction. There's only one thing here that fits that. The iodate. Why does the iodide, I negative, not fit that?
Because it's not an overall reaction.
Okay, well, it's not an overall, but it's not produced in one and used in a later. Do you guys see it's there to start with, and it's regenerated at the end? It's coming back. It's ready to be used again. Do y'all know what I negative is?
It's isotope in it.
It's an ion. I'm asking in terms of this.
Iodide?
It is iodide. Those are all right answers. It's just not the one I'm looking for. It's a catalyst. It's a catalyst, because catalysts speed up a reaction and that they are not used up. So it's regenerated, ready to be used again. Okay, trust me, it's a catalyst. I see y'all like, okay, whatever, that's not what I was gonna say, but that's what it is. I negative is a catalyst. What if I told you that the rate law, oh, I can't tell you that on this one. I need the rate law for the overall reaction. That's a question. Is blank. And I would write up here by these steps that the first one is fast. And the second one is slow. So what's the rate law going to look like then? It's got to match the second equation, right? Because it always matches the slow step. You would include the intermediate in it. So that's the answer for that one. All right. Guys, that concludes chapter 14.
I thought that meant the day.
That's what I was going.
Give me 5 more minutes. 5 more minutes, okay? Chapter 14, into chapter problems. Because I want to talk to y'all about what I just gave you. These start on page 652. When's that connect due? Is it due this Friday for chapter 14? Next Friday? Okay.
Have you even touched it yet?
I was about to say, I haven't even opened it yet.
I don't know. Wesley said
It's the
next Friday.
18th.
Okay.
Thank God. What a blessing.
Okay.
That's
Oh, I'm so glad that I'm making y'all so happy.
You made my
Y'all
day.
remember that, okay?
Made my day.
Good. 5, 15, 17, 19, 27, 29, 31, 59, 61. That may be it. Do a thing. I'm gonna throw in 111 because I like that one.
I mean, it's gonna be on the first page. We're still right now.
It's really hard, maybe I find.
Yeah.
It's not hard, it's just looking at a graph, at a diagram. Okay, let's talk about what I got for you here. Okay, this is kind of like a take-home lab.